Let's try some variations on a new question. What is the tag set in Word? How many bits make up the tag and the set in the word? For this system, 1 cell per word main memory, 1 megabyte total main memory with an 18-bit address. The cache is an 8-way set associative cache, 2 kilobytes total cache, and there are 16 words in a line. And finally, which set does cell 1031 go into? Okay, first let's figure out the tag set in Word. We know the whole thing has to be 18 bits because the main memory address is 18 bits. Tag set word. There are 16 words in a line. Take the logarithm of that, and we'll find that it takes 4 bits to address a single word in a line. If there's 2 to the 20 bytes per main memory, and I divide that by 2 to the 11 bytes per cache, then I get 2 to the 9 caches per memory. Usually, with the questions we're familiar with a direct mapped cache, we can take that logarithm and say that's the tag, but not anymore. Now it's going to be 9 plus the log base 2 of 8, this. In the last video, I was explaining that's a measure of how much competition there is. There are more competition because however many lines there are 1/8 as many sets. So the blocks are fighting for 1/8 fewer things. So this is going to be 12 bits. So I'm up to 16, 12 plus 4. So there's 2 left. Let's see if that adds up correctly, literally. I'm going to check, are there really 4 sets? Well, let's say 16 words per line. How big is a line? I mean, how big is a word? 2 to the 20 bytes per memory divided by 2 to the 18 addresses per memory gives us 2 to the 2 bytes per address, or bytes per cell, because it's the cell that has the address, or bytes per word. 2 to the 2 bytes per word. So now, if there are 2 to the 11 bytes per cache, and I divide that by 2 to the 2 bytes per word, then I find out there are 2 to the 9 words per cache. So I'm trying to find out here, are there really 4 sets? Times 8, so it should be 32 lines total. So let's see what else I have to do. 2 to the 9 words per cache divided by 2 to the 4 words per line. I'm just looking at the units here, and I get 2 to the 5 lines per cache divided by 2 to the 3 sets. No, lines per set is equal to 2 to the 2 sets per cache. Take that logarithm, and that tells us how many sets there are. So I just double checked our work. That's what I did. This seems to be correct. Which set does cell 1031 go into? Well, there's a bunch of ways of figuring this out. I could write 1031 in binary. Let's try that. That's 1024 plus 7. So that's 2 to the 10. 1024, there's one of those. No 512, 256, 128, 64, 32, 16, or 8. But there is a 4, a 2, and a 1. This is 1024 plus 4 plus 2 plus 1 is 1031. So if I write the cell address in binary, take the last 4 bits. This is word number 7, the 8th word, but word number 7 in its line. The next two bits are the set. So it's in set 0. And then the tag is 1, 2, 4, 8, 16. Tag 16. Set 0. There's 8 choices. Every set has 8 lines. So when it first goes in there, it will have replaced the least recently used line, for example. And then the word is 7. Another way of solving this is to find out what block this is in. So that's one way of solving it. The answer is set 0. Cell 31, and there are 16 words per line. I can divide 1031 by 16, which is basically 2 to the 10 divided by 2 to the 4 is 2 to the 6, 64. Remainder, 7. There's the 7. And the 64, that's the block number in main memory. And to find out, so it's 64. And if I do 64 mod, how many sets there are? There's 4. So block 64 could go in sets 0, 1, 2, or 3. This is indicating there are 4 sets. And it goes into that one. Set 0, which confirms what we had here. That's how we can answer those 2 questions. Before you start the next video, try solving this for a 4-way set associative cache.